So, good morning. Now that I've restarted the recording, today we're going to start trudging a little into Chapter 6, which deals a lot of single and multi-component phase equilibrium, material balances. There's a lot of things looking into Gibbs-Phase rule, Routh's law, Henry's law, crystallization. There's a lot of stuff in Chapter 6, and so that's part of why I quickly jumped through chapter 5, because chapter 5 is just looking at equations of state. And for those of you in chemical engineering, we have another course that we get to spend looking at a bunch of equations of state. So I let that course do that. I just like to give you guys a flavor in terms of, really more importantly, the ideal gas equation, because it's really important in doing calculations, being able to make that assumption and then correct for it. But before we jump into the chapter 6 material, there's one thing I did want to bring in your attention, primarily because I didn't touch base on it on Wednesday. But it's looking at non-ideal gas mixtures. And so there's some special things that we have to consider for non-ideal gas mixtures. Primarily as it refers to trying to figure out properties of these mixtures. And so we had talked about looking at the compressibility charts. In that you have to look at your reduced pressure and your reduced temperature for a single component, right? Which is the pressure over the critical pressure, the temperature of the critical pressure. But for a mixture, you're going to have multiple components, each with their own critical temperature and pressure. And so the question then becomes, how do I use the compressibility equation of state in the charts to get an idea of these variables when I have multiple components? And so what we fall back on is what's known as ChE's rule for non-ideal mixtures. And what ChE's rules allow is to come up with what's known as a pseudocritical temperature and pressure for a mixture. So we call them TC prime, PC prime, because they're not a true critical temperature and pressure, but they're kind of an approximation for the mixture as a whole. And ChE's rule says that these pseudocritical values are essentially a mole fraction of your component times the critical temperature of that component. And the same thing with the pressure. And so what you do is you kind of approximate that in relation to each species in the mixture. And so with that, you get an idea of what those values are. And then the pseudocritical reduced temperature is just the actual temperature over that pseudocritical temperature. And the pseudocritical reduced pressure is the actual pressure over the pseudocritical pressure. And so basically, if you're using the compressibility equation of state with non-ideal mixtures, you calculate these values, TC prime, PC prime, then you calculate the TR prime, PR prime, then you use the charts to find Z. And then with Z, you can calculate the mixture's molar volume. And then with the molar volume of the mixture, you can then find out some information. And I wanted to point this out primarily because on your homework that's due today, pretty sure it's due today. Yeah. This is a method you're going to have to use for one of the problems. So you're going to have to find the pseudocritical values, pseudocritical reduced values, find your Z, calculate V sub M, and then with V sub M, you can answer the questions in the problem. But are there any questions on that or anything in particular to chapter 5, ideal gas equation, non-ideal gas equations of state? Like I said, I didn't want to bog you down with it, primarily because there's a lot of things we can get lost in when we're talking about non-ideal gas equations of state, and you know which equation to use for what component. But the whole purpose of that is to see the ideal gas equation and apply it to material balance equations, and to get some idea of what to do when the system can't be considered ideal. No? All right. So let's start looking at the final chapter of this course. Chapter 6, looking at multiphase systems, and talk about how we can apply phase equilibrium to material balance problems. So when looking at a multiphase system, one of the things that becomes primarily important is our use of phase diagrams. And I know we've seen these when we talked about non-ideal gas equations of state, but it's important because it allows us to consider which phases may be present as a function of both temperature and pressure. Now, if we're looking at a single component, all we really need to look at is this phase diagram. And it allows us to understand the implications of manipulating process variables and how it's going to affect the presence and influence of phases. For example, this is where we like to do a lot of piston cylinder things. If I've got a piston cylinder, and I've got some liquid water and some water vapor, it's going to exist at some pressure, temperature, and occupy some volume. And if the piston moves down, what will happen to the system? So what are the implications of moving that piston down and decreasing that headspace above the liquid?
Maybe the pressure will go up.
So the pressure may increase?
Maybe.
Question mark. So maybe. I like that.
You have a change in volume.
Well, we should have a change in volume, right? So this piston might kind of move down here. So the vapor will occupy less volume, potentially, right? And one thing I'm going to say is I'm going to assume this was all at equilibrium. Well, let's look at the ideal gas equation and see what we can come up with. So if I lower that, just the number of moles are T, and I'm going to assume, well, I didn't say anything about temperature, but I'm going to assume it's isothermal. And I said the volume's going to decrease, right? Because if the piston moves down, that volume's going to fall. So the V2 is less than V1. T2 is equal to T1. R is R, right? So the question then becomes, what happens to P? And what happens to N? Right? And so we can say, well, if in this case, if the volume decreases, one of two things has to happen. Either the pressure has to increase to compensate, or the number of moles must decrease. So which one? So what do you guys think? Is it going to be pressure that's going to change, or the number of moles that's going to change?
It'll be pressure.
So I got to vote for pressure. One vote here. Anyone else vote for pressure? Mitch, you were on the fence earlier.
I think pressure.
All right, I got another for pressure.
Pressure.
I'll go for pressure too.
All right. So I got a lot of votes for pressure. Well, let's take a look at one other equation and see if we can get more information out of it. Primarily looking at, what's the equation called? Every equation's got a name. That's it. Oh, it doesn't have a name. Well, do you guys remember this expression that we had talked about? Where the partial pressure of a component was equal to the mole fraction of the component times the total pressure. Right? And so this tells us a couple things. If the headspace is pure water vapor, yi would be 1, right? And so the partial pressure of the system is equal to the total pressure, right? If I'm saying everything is pure water vapor. And in that case, if the partial pressure is the total pressure, this question's not so straightforward to answer, primarily because if I increase the pressure of the system, I have to increase the partial pressure of the water vapor. And if I have to increase the partial pressure of the water vapor, my system will no longer be in equilibrium. So what has to happen in my system is as I increase this pressure, my equilibrium is going to fall out of balance. In order to reobtain equilibrium, some of the water vapor will have to join the liquid phase. So this answer is tricky because in a lot of ways, both of these things are going to occur because the number of moles or the amount of water vapor is going to decrease as that pressure increases to maintain equilibrium. And let's look at the phase diagram, right? So if I was at a particular temperature and pressure and I have liquid and vapor present, I'm going to be on this equilibrium line. And if I try to increase my pressure, I'm going to move away from that equilibrium and I'm going to force things into the liquid phase. Does that make sense? And what that tells me is if I'm on this equilibrium line, in order to increase my pressure, I would most likely have to liquefy all of the vapor present before I can move into that liquid state. Which means essentially that this pressure would not increase until the number of moles in the vapor phase went to 0. Because if I'm at this line, my partial pressure is equal to my saturation pressure. And I can't move beyond that until the phase transition has fully taken place. Does that make sense, or is it a little confusing? And it's okay if it's confusing. So let me recap for that for you. So we had this piston with vapor and liquid in equilibrium. And if the piston moved down, the question was what happens to the system? Well, by the ideal gas law, if it's an isothermal process and my ideal gas constant doesn't change, but if I move the piston down, the volume's going to change. And so that leaves either the pressure or the number of moles to change to compensate for that volume. But based on this expression where the partial pressure is equal to the mole fraction times the total pressure, for the total pressure to change, the partial pressure has to change. And since the system's at equilibrium, the partial pressure is gonna be at a saturation pressure. And so what's more likely gonna happen is the number of moles in the vapor space is gonna enter the liquid. And so the number of moles is more likely to gonna decrease to compensate for the volume. The pressure will only increase when all of the vapor has entered the liquid phase, which it really largely depends on the degree of the volume. But if it's just a small change, only some of it will join the liquid phase and not all. Primarily due to this vapid liquid equilibrium, because we'd be at this point and we would be trying to go this way. So it's always important to consider, especially when you're looking at pure component systems, the implications of moving away from these equilibrium lines and overall in terms of the phases involved. Any questions on that? Well, if I don't have any questions, we can keep moving a little bit. And now let's talk about volatility and vapor pressure. So volatility, simply defined, is the tendency for a substance to transfer from a liquid state to a vapor state. And volatility is largely quantified by a substance vapor pressure. And so looking at that system that we had earlier, if I had some liquid, right? I have the presence of vapor and liquid. And so the tendency of that water to enter the vapor state is known as its vapor pressure. And if the liquid and vapor are present at equilibrium, that vapor pressure is equal to that saturation pressure. And so you're looking at a saturation point. And if you're not at saturate, if your vapor pressure isn't the saturation pressure, then you are not at equilibrium. That's part of why that question earlier was a little tricky, because since both are present and since I said it was equilibrium, that's why these kind of special cases emerge. So then how do we calculate vapor pressure? Well, there's a number of ways in which we can do it. One way is through what's known as the Clapeyron equation. Which states the relationship between a vapor pressure, P star, and here I'll try to be consistent. Do you guys like P star for vapor pressure or P vape? I like to let students decide. All right, well, I'm going to use PVAP. Didn't hear anything. So the relationship between your vapor pressure as a function of temperature by the Clapeyron equation is the enthalpy of vaporization, also known as delta H vape, divided by the absolute temperature times the difference between the molar volume of the gas of the species minus the molar volume of the liquid species. Meaning the vapor pressure as a function of temperature is largely determined by the energy required to vaporize your substance over the volume requirements to move the substance from the liquid state to the vapor state. And so in the grand scheme of things, it falls into an energy balance system where the energy available, which is largely a function of the temperature, the species balances itself as a function of the vapor, the volume available, as well as the energy required to vaporize that substance. And like I said, this delta H vape, latent heat of vaporization, T is your absolute temperature. V hat sub G is your molar volume of the gas. And the V hat sub L is the molar volume of the liquid. Another approximation for this is through what's known as the Clausius-Clapeyron equation. Which is a modified form that linearizes the Clapeyron equation above. We have ln of p vape equals the negative delta H V over RT plus B, where B is an empirical constant. And it's unique to each species.
Is that value in the back of the book or is it in the chapter?
That's a good question. Typically, I don't believe we have Clausius-Clapeyron values in the back of the book. You might find it online and in things like Perry's, but yeah, I would be hard pressed. A lot of times it's determined via experiment, and so I don't think this book has those values published in it. And primarily because there's another method that we use more often, which the book has those constants published on. But you know, the Clausius-Clapeyron is useful primarily because if you look at this system, and if we graphed essentially ln of p vape versus 1 over t, we would get a system that looks like this. Where this slope would be delta h v over r. And this intercept would be b. And so it's useful in that it's a good way to get vapor pressures experimentally, primarily because you can take data, graph it, find the constant, and then use that going forward to estimate vapor pressures at varying temperatures for a particular substance. So let's look at a quick example using this equation. It's from the book and on the lecture. It's based on this data, estimate the latent heat of vaporization and B value for an unknown substance, and use the Clausius-Clapeyron equation to estimate the vapor pressure at 4 to 45 millimeters of mercury. So the data that we have, it's P in millimeters of mercury, vape times T, which I believe is in C, 40, 60, 10, and 17.4. So you'd have to look at the absolute temperature, which 10 degrees is about 281 Kelvin. Oh, did I say that was 10 degrees? I did. That's 283. And 17.4 is what? $290.4. So the easiest way to do a problem like this is most definitely Excel. So I'm going to pop over to Excel. I'll share that screen with you as soon as my Excel has effectively loaded. All right, so you should be able to see my Excel. So we had pressure in millimeters of mercury, temperature in Celsius, temperature in Kelvin. I like how it auto thinks I want to copyright something. And we need 1 over temperature. in terms of Kelvin. So if this was, you would generate a quick plot. And you would want to create a plot. I like how it thinks it knows what data I want. So on your x-axis would be 1 over temperature. Your y-axis should be the pressure. You should get something that you can draw a line through. Luckily, Excel's a nice way to do trend line. So keeping in mind that the y-axis is in terms of millimeters of mercury, and the x-axis is in terms of 1 over temperature. And its units are 1 over Kelvin. And so it becomes really important, primarily when you go to calculate the slope enthalpy of vaporization. You want to make sure you get those units right. So from that, doing that quick plot, I got an expression that says y equals negative 216421 x plus 804.74. So with this, hopefully, I should be able to estimate my enthalpy of vaporization as well as my B value. So this is where I would probably say from Excel, y equals negative 216421 plus 804.74. Keeping in mind this negative 216421 is equal to negative delta H vape over RT, over R. And the 804.74 is equal to B. Right? And so like I said, this was 1 over T. So there's a 1 over Kelvin there, right? So if I set R equal to 8.314 joules per mole Kelvin, that will give me my enthalpy of vaporization in units of joules per mole. Which from this, I would take the 216421 times 8.314, and then I would divide it by 1,000 because that number is fairly big. And then that would tell me my delta H vape is equal to 1,799 kilojoules per mole, since I divided by 1,000. And to find my units of B, since my Y is in millimeters of mercury, and my first term has no units once it's all canceled out, that tells me my B value must be in millimeters of mercury. Is there any questions on how we came up with that? So now I have the latent heat of vaporization in kilojoules per mole and my B value in millimeters of mercury. The last thing that we can look at is to estimate the vaporization pressure at 45 millimeters of mercury. Oh, actually, that means the temperature. To get a vapor pressure of 45 millimeters of mercury. I wrote that wrong. I apologize. So that means if Y is 45 millimeters of mercury, then I have 1799 negative over 8.314 times 1 over T plus 804.74 millimeters of mercury. So doing that math, we can see what we get. So if you do that, you should get about, for T, 285 Kelvin, which is about 11.8 degrees Celsius. Is there any questions on that? All right, if there's no questions, we'll keep moving to another way of calculating the vapor pressure, and I would argue it's probably one of the most common, and it's through use of what's known as the Antoine's equation. And this is just a simple empirical method. I shouldn't say simple, that doesn't really help you. For estimating the vapor pressures of species. And Antoine's equation looks like this: log PVAP equals A minus B over T plus C, where T is the absolute temperature, and A, B, and C are empirical constants. Now, I will tell you to be careful with Antoine's equation a little bit, because sometimes it's reported as a log and sometimes it's provided as a natural log. So it's always important when you're looking at a table of Antoine's equation constants, what are the units of both vapor pressure and temperature that it goes with. You have to be consistent or your calculations are going to be off. Now, in the back of the book, and I believe it's in Appendix B, and it's Appendix, I think B3, oh no, B4, or at least in the third edition, it's B4. There's a table of Antoine equation constants for various substances. And it's a pretty extensive list. And you'll note that it gives you the equation and it tells you what are the units of vapor pressure that it spits out and what are the temperatures that you have to put in it. For example, the one in the back of this third edition, the temperature has to be in degrees Celsius. And so, I say temperature is absolute, but sometimes the constants are adjusted to allow relative values. So you just have to make sure you have to be consistent. And also you'll note in that table, sometimes the same substance is listed more than once, but for different temperature ranges. And so you always want to make sure that you're using the right constants for the right substance and also for the right temperature range of that substance. But it's really common because it's a nice straightforward way of determining vapor pressures. So let's look at a quick example. And I would say if I had to estimate the vapor pressure of N-hexane at 34 degrees Celsius. Well, what I would probably do is go to that table I stated before. And if you look up hexane, N-hexane, you would find these constants. So all right, from table B.4, A for N-hexane is 6.88555. B is 1175.817. And C is 224.867. And note, it's a log equation that gives P-vape following this form, where T is in degrees C, and the P-vape it gives is in millimeters of mercury. So I'm looking at 34 degrees C. So log of P-vape equals 6.88555 minus 1175.817 over 34 degrees Celsius plus 224.867.
What edition did you say this numbers come from?
It's in both editions. The one I have here is the third edition, but it should be in Appendix B in the back of the book. It just may not be Table B4, but there's a table of contents for Appendix B, and you just need to look up where it says Antoine constants for various substances. So you do this calculation, and you get P-vape is equal to approximately 220.5 millimeters of mercury. Is there any questions on some of these calculations? One other way that you can do it, it's not as common. Like I said, Antoine's typically what I use, if I'm honest, is what's known as the Cox charts. It essentially lists as a function of temperature and vapor pressure, various species. And it's kind of a graphical way to estimate vapor pressure, but the major issue of the Cox charts is that since it's graphical, it's prone to a lot more error because while engineers really like charts, charts aren't the most accurate way of doing things, especially for calculations, because one person's straight line is different from another person's straight line. The last thing I want to talk about today is really the Gibbs-Phase rule. And the Gibbs-Phase rule gives you a relationship for systems at equilibrium between degrees of freedom, the components, and the phases involved. And so the Gibbs-Phase rule states that the number of degrees of freedom, I'm going to write DF here because I like to delineate it from the chapter 4 degrees of freedom. It's 2 plus the number of components minus the number of phases involved. And it's important to note this only applies when the system is at equilibrium. Like I said, C is the number of components or species. Pi is the number of phases.
I have a question.
Yes.
Whenever you say equilibrium, that means the the P vaporization value is the same as what you find in the back of the book. What do you mean by equilibrium? Like,
Equilibrium meaning the species, the number of moles between phases is not changing with time. For example, if I have a glass of acetone in air and it's open to the air, the acetone over time is just going to all vaporize. But if I close that container, the acetone in that air space above the liquid acetone, it's going to vaporize until the vapor pressure of acetone in that headspace equals the saturation pressure. And at that point, there's no more ability of that vapor space to hold acetone. And so that system reaches an equilibrium because the vapor pressure equals the saturation pressure.
alrighty, thank you.
Of course. And so looking and applying the Gibbs-Phase rule, for example, if I have one component and 2 phases, that means the degrees of freedom in this system is 2 plus 1 minus 2, which is 1. That tells me I need to specify a variable. Well, let's look back to that phase diagram. So if I'm at equilibrium and I have 2 phases, that's only going to occur on one of these lines. You see that? And so by specifying the temperature or the pressure, right? And if I know the phases, I've already specified the other variables in the system, right? If I specify the pressure, I've specified the temperature at the same time. if I know I have 2 phases. And at the same time, if I say I have 3 phases, then you don't need to state what the temperature and pressure are, because there's only one point in which 3 phases can be present, which is that triple point. But if I have, let's say, 1 phase, then my degrees of freedom are 2, and I have to specify both the pressure and temperature for that system to be fully specified. And at the same time, the more components specified, the less information I need. Because once again, equilibrium allows that to inform us what is necessary. Right? And so example, if I have 2 components and 2 phases, the degrees of freedom will be 2 plus 2 minus 2, which is 2. So I need to specify temperature and pressure to fully specify that system. Does that make sense? Are there any questions on that? No? All right, well then that's what I have for you guys today. I'll go ahead and stop it there. Don't forget your homework 5, I believe, as well as the quiz 5 are due tonight at midnight. So try to get those in. If you have questions, I'll be on this afternoon for office hours. And if you guys don't have questions, I hope you guys have a great weekend.
Have a good weekend.
You too. Oh, it's actually, I should say quiz 4 is due Friday. Quiz 5 will be due Sunday. Quiz 4 is due today. I pushed quiz 4 back. And then homework 5 is due today. And homework 5 is primarily over chapter 5 material. All right, take care, guys.